Hi guys, in this video we're going to talk some about the periodic table, and then really that's what most of this chapter is about, just elements and the periodic table, things like that. So just remember that atoms make up everything. We've already discussed that. There's atoms in the air, there's atoms in the rock, things like that. Okay, so we know that atoms are incredibly small. A single pebble will contain more than you can count, and the number of atoms far exceeds the number of pebbles that are in the San Francisco Bay. So they're very, very, very tiny. Okay, so it takes a very large number of atoms to make up just one pebble. So think of how many would make up Mount Everest. Okay, so just remember, atoms make up everything. They compose matter. Okay, an atom is the smallest identifiable unit of an element. Okay, and elements are found on the periodic table, which we'll talk more about in part 2 for chapter 4. But just remember from last chapter, chapter 3, elements can't be broken down into simpler substances. Okay, there are natural elements and there are synthetic elements. And then the exact number of naturally occurring elements is controversial. But we have discovered some now that we thought were synthetic that we now can't actually find in nature. So this is called atomic theory. You are going to need to know these key people. Democritus is first. He was in, 400-ish BC. Okay, and he said that if you divide matter into smaller and smaller pieces, you're going to end up with these tiny indestructible particles, which he called atomos, or atoms, in Latin, or Greek. It may have been Greek. And that just meant indivisible, so they're not able to be broken, which is that indestructible part. Okay, you are going to need to know the order, so make sure you write them down and you keep track of the order. So again, Democritus was in the 400 BC range. Dalton was next, so we skipped 2,000 years. Okay, and Dalton had an atomic theory, so what he did was took other people's theories. There were some people in between, but not very many. And he put it all together into one cohesive theory. So he took Democritus's idea that each element is composed of these tiny indestructible particles that we call atoms now. He also said that atoms of a given element have the same mass and other properties that distinguish them from other elements. And he said atoms combine in simple whole number ratios to form compounds. Okay, we will talk about this, but as we go through, number 2 is going to have an issue with this same mass. Okay, and again, we'll talk about that. I believe that's part 3 that we're going to discuss things like that. Okay, this is just showing they've got scanning microscopes and they spelled out IBM with atoms to be fun. It is xenon, and xenon is a fairly large atom in comparison to others. So, okay, next person after Dalton is J.J. Thomson. And you need to know that he is responsible for discovering the electron. And he used a cathode ray, which we'll see on the next slide. But what he did was that the cathode ray was shot, and there were electrodes, not really electrodes, but charged plates. And the charged particles got deflected, the negative ones did, towards the positive plate. And so then he was able to discover, hey, there's electrons or something negative in here because they were attracted to the positive plate. Okay, so he said that atoms must contain a positive charge that balance the negative charges that he found. And he is responsible for the plum pudding model. And the picture is above. Okay, this was a common thing back in the 1800s. Early 1900s, plum pudding in England, but now I would kind of say it's like a chocolate chip cookie. So the batter of this cookie is positive, and the electrons are the negatively charged chocolate chips, and they're just kind of scattered throughout the cookie. They're not really in any clouds, in any shells, anything like that. They're just present. Rutherford was next. He used the gold foil experiment. So he shot alpha particles at gold foil. He believed that they would go straight through if the plum pudding model was correct, but some of them bounced back. Basically, what happened when they bounced back, you can see in this bottom image on the right, some of them hit the nucleus and bounced off or got deflected. Okay, so he decided there must be something small and dense in the center of the atom. Okay, so most of the atom's mass and all of its positive charge are in the small, dense center called the nucleus. Most of the volume is empty space, which is accurate. Okay, and that's where our electrons are, in this empty space. So this is kind of like our electron cloud that we know of now. We also knew it was charge neutral. Okay, so our protons must equal our electrons in order to have no charge. Okay, as far as the empty space goes, y'all, this is lots and lots and lots of empty space. Okay, if we were to use Cowboy Stadium as an example, if you put a marble on the 50-yard line, a normal-sized marble, that would be the nucleus, and the rest of Cowboy Stadium would be the empty space. Okay, so tons and tons of space is empty in the atom. That's what Rutherford said. And his model is called the nuclear model because it has a nucleus. Okay, also just remember that electrons don't have much mass. Most of the mass is from the nucleus. Okay, so here's our example. If the proton had the mass of a baseball, an electron would be like a grain of rice, which is about 2,000 times less massive than the baseball. Okay, so very, very, very minuscule. Also, just remember those positive and negative charges attract, opposites attract, and if they have the same charge, they're going to repel. So if we have positive, positive, they repel. If we have negative, negative, they repel. But those positive and negative charges are going to attract to one another, and when those are involved with each other, they become charge neutral, or their charge equals 0. So we now know that protons and neutrons have very similar masses. And if we look here on this chart, there's our masses, and electrons have almost no mass. So we really say this is 1, 1, and 0. Again, electrons do have mass, it's just really, really, really small. Also, make sure you know their charges. You should know that from middle school. If you've forgotten, write them down. Protons are positive, neutrons are 0, electrons are negative. Okay, so electrical storms provide evidence of charges in nature. So most matter is going to be charge neutral, so it's going to have no charge. So it'll have equal positive and equal negative so that they cancel out. But in an electrical storm, the charge balance is disturbed. And so that lightning coming down from the sky is that rebalancing of the charges. Okay, so how do elements differ from one to another? So just remember that elements are defined by their number of protons, which is also the atomic number, or Z. Capital Z is the abbreviation. And the atomic number is the top number on the periodic table. It's a whole number, it's going to be the smaller number. Okay, almost always it is the top number on the periodic table. And you can see it here. Okay, so most chemicals are based on their English names, although some were discovered in other countries, so they got names according to those. So some have Latin names, some have Greek names. There's even some with German names. But if they're weird, it's because they were named in another language and we translated them. Like lead is plumbum, which is why it's PB. Okay, and iron is ferrum, which is why it's Fe. Things like that. Some of them are named based on their reactivity or their properties. So argon means inactive in Greek. Some were named after countries. Some were named after scientists. But regardless, all of their atomic numbers equal the protons in that specific element. So like curium, for instance, was named after Madame Curie. Bromine is named that because bromos in Greek means stench. And bromine specifically has a very strong odor or smell. All right, so here we're looking at our periodic table. So I have posted one in this chapter. You can look there, or you can look in your book. It should show you. Okay, so silicon is Si, and Si is element 14. Potassium is K, element 19. Gold is Au, and that is 79. And antimony is Sb, and that's 51. So it's going to take y'all some time to get familiar with it, but you're going to need to be familiar with the periodic table because questions like these should be super easy ones. Okay? Also, by next year, if you decide to take AP Chemistry, which is needed for, so yes, this chemistry class counts for college, but it's not the chemistry class you need if you want to major in any type of science, any type of engineering, not just chemical. All engineering students need chemistry and not this introduction one, the general one. And if you want to go in the health field. Okay, so if that is you, you need to start thinking, can I take AP Chemistry? And even if I'm struggling now, it's going to get easier. And as we go along, things are going to start to click. But it's going to be better to take it next year as a junior than it is to wait till your senior year or even wait till you get to college. Once you're in AP Chemistry, our periodic tables no longer have names, but we will have used them so much, you'll know their names for most of them. Now, not the random ones, but most of them you will know. Okay? Another thing you need to keep in mind, normally I make students memorize the major elements that we use. It's about 30 of them. Their names and their symbols. So, and that's normally like day 2, we take a quiz on that. Obviously, we're not doing that this year because this year is a different environment, but just keep in mind, you're going to need to be very, very familiar with the periodic table if you're not already. Okay, so Na is sodium, and that's element 11. Ni is nickel. Nickel is element 28. P is phosphorus. Phosphorus is 15. And Ta is tantalum. And that's element 73. Okay, I do want y'all to keep in mind also that elements are not proper nouns. Okay, so generally we don't capitalize them. Whew. I'm not saying I'm going to count off if you do, but I do need you to keep in mind that these are not proper nouns. All right, and that's it for today. If y'all have questions, please let me know. I'm thinking we won't have too many on this though. Okay, y'all have a great day.